So, we've got some things due. I've shifted some due dates as of last night. They should be up to date in LoudCloud, right? So System ID Lab is not due on Wednesday anymore. It's due on Sunday. It's due on Sunday. So you got a couple extra days there. Instead of homework, all right, so Lab 3, there is a video about Lab 3 on YouTube, right? So check it out. Also, I posted the document for Lab 3 that you need to do it. So check that out. I made an executive decision, and instead of having you guys do 2 more homeworks, I'm going to have you do 1 more homework that's going to be shorter than both homeworks 6 and 7 combined, but worth twice the points. That will be due on the 13th. Okay? So homework 6 and 7 is now mega homework 6 and 7 together. There will be a theory section and some problems. That got posted last night as well in LoudCloud, so check it out. That's due on the 13th. Okay, you've got a couple weeks there. Exam is on the 17th, which is the last day of class. A benchmark assignment, it won't let me move. So it's still going to tell you that it's due on the 13th, but just turn it on the 20th, which is the last Sunday of the semester, the very last day of the semester. Turn it in. My other executive decision was, rather than take time in class to discuss the benchmark, I made a video discussing the benchmark that is also on YouTube. Please watch it and ask me if you have any questions regarding the benchmark. It's a pretty straightforward project. I went through and described what the expectations are, so please watch the video. Okay, there's a rubric for said video, so that's fine. The presentation is also due on the 20th. What you guys have to do, that's discussed in the video as well, but what you guys have to do is either screencast yourselves with a PowerPoint doing it and submit a link to a YouTube video of it. Right? You can make it private, submit your slides as the deliverable with the link to your video on the slides. Okay. Other than that, office hours today have been canceled. I told the last class, I told some of you guys before class about I had to bring my dog to the vet this morning. They said he's all good and everything, but because of that, I'm the only one that can pick him up, and that they close at 4, so I have to leave here as soon as class is over to go pick him up. Otherwise, I'm pretty sure they take the dog away and you don't ever see him again, or either that or you pay exorbitant fees to get him back the next day because he then has to stay at the vet's in the vet. So we'll just go get him. So. Okay. Any questions on what's due? This is it. This is the rest of the assignments for the whole semester, right? This is all of it. We've got 3 weeks. Yeah, okay. Yeah, good question. So exam 3 right now, the plan is to do test models again like last time. I think it worked out pretty well, and yeah, it seems to be doing all right. So we'll keep that up. Exam 3 is the final exam, but that doesn't mean that it's a final exam. So what do I mean? It's not explicitly going to ask you one question from each section. It's not cumulative in the sense that I expect you to have knowledge. Well, I mean, I do expect you to have knowledge of all the topics, but I'm not testing you on the other topics. This is going to focus mostly on topic 6, the same way that the last exam focused on time domain and Laplace transform, right? But as you guys know, this class has been building since day 1. And all of the things that we learned in modeling still apply to frequency response analysis, right? So everything that we do is going to be geared towards that, okay? So like the theory section is going to be on topic 6 stuff, right? Okay. Any other questions?
I have a semi-specific question about Lab 3, but it might be in the video, but I don't think it will be.
What's your question, Toby?
So from the lab, from at least my math, and it could be wrong, my overshoot for that diagram was like over 100%, so it made my dampening ratio negative, and the dampening ratio should be between 0 and 1, right? So is that even right, or did I screw up?
The damping ratio should never be negative.
Right,
There's,
but I think when that maximum overshoot goes over 100%, though, I think that just makes the dampening ratio negative because of the math.
Right. So
I had the same problem.
okay. Come to office hours tomorrow so I can take a look at it.
Okay.
So, any other questions? Well, in that case, I'm going to find my clicker over here. Very good. And we're going to talk about frequency response analysis, right? So we covered time domain. Now it's time to get into frequency domain. What are the topic objectives, right? What do we want to be able to do? We want to be able to draw the frequency response graphs for a transfer function. Right? We want to determine the steady state response to a sinusoidal input using the graph or transfer function itself. We want to calculate resonant frequencies and determine the bandwidth for systems. We want to evaluate vibration isolation systems for the effects of base motion and rotation on balance. And we want to solve the steady state behavior of periodic inputs when given a Fourier series representation of the output. Now remember from that video when we were talking about Laplace transform, right? The Laplace transform is a slice of the Fourier transform, right? It's a slice of the Fourier series. So it's most likely going to be geared toward that, right? So we've discussed in detail how to analyze several input functions, right? So what are they? What are the input functions that we have been pretty much sticking to this point? What input functions do we typically use?
Step and ramp.
Ramp and what was it?
Step.
Step, yeah, those are two of them, sure. A couple others. Impulse,
Sine.
yeah.
Pulse.
One more, and you get it. You got impulse, you got ramp, you got step. There's the one that we use to derive the impulse. You guys remember that one? What's that one? Just a regular pulse, exactly. Right, we've got these four, right? We've been talking about these. We haven't really been talking about how to do sine inputs though, right? Sinusoids. We use them in the homework. We test systems to them, but we haven't really talked about any of the mathematics behind calculating their response, right? But that's going to change because it's really important for us to be able to analyze a system's response to a periodic input. Some of the examples of this are unbalanced rotating machinery, which causes vibration, noise in electromechanical systems, vehicle dynamics and vibrations, and wing flutter. So you might be noticing something. It's mostly things that cause vibrational or noisy issues, right? We want to learn how to handle these in our input response. Right? Unbalanced and rotating machinery, right? So I don't think I told this class the story, but before college, in the summer before college, I worked at a beach amusement park, right, in New Jersey. I was the tilt-a-whirl / scrambler operator. Real high point in my career. I'll still list it on my resume. Right? But you know, it's pretty standard job, right? It's like pull the lever and it goes, or press the button and it goes, right? And that does that, right? But there's one job that nobody really ever wanted to do, which was the Ferris wheel. Okay. Because when you're doing the Ferris wheel, you have to load the Ferris wheel proportional to what each to across, right? Because you can't have any rotating unbalance. Because if you have rotating unbalance, one side will be heavier than the other. You will then cause issues with your bolted connections. And you end up with a Simpsons-like situation where the Ferris wheel pops off and rolls down the beach, right? Except that it's funny in The Simpsons, is not funny in real life, right? And just to keep this in mind, this is a bunch of high school / college kids who are running these things, right? So super safe environment. But anyway, rotating imbalance is really important, right? More so in actual machinery in like in a shop or on an assembly line where we're going to get excess vibrations. How do we handle these vibrational inputs? So how do we model these repeating inputs? Well, here it is. U of t is equal to U naught sine of omega t, where U naught is the amplitude and omega is the frequency in radians per second. Just as a reminder, if you're given something in hertz, you're going to need to convert it to radians per second. How do we do that? We multiply by 2 pi. Okay. Multiply by 2 pi. This is probably a good time for me to tell you, give you the public service announcement, that if your calculator is in degrees, from this point on, you should have it in radians. Okay. It's gonna throw you off otherwise. Make sure you're in radians when you're doing this stuff. Sean, the benchmark assignment is individual by nature, as the way that the school sets it up. Also, lab 3 is individual too, right? You guys, no group work on lab 3. No individual report. Okay? So yeah, the benchmark is an individual assignment. All right. So here's the equation for a sine wave input, right? What if I had a cosine? Well, it would look like this, but with a cosine. Okay, great. So what do we do with it? What do we do with it? Well, if I'm given a sinusoidal input, then my system's going to oscillate at the beginning at both the natural frequency and the input frequency, right? So imagine, right, the natural dynamics in the system still apply. So I have this natural frequency that it's vibrating at, right? But I also have this additional input frequency that's going to add to that vibration, right? And this is the transient response. Maybe some of the models that you made for homework, right, where we put in a sine wave, you might have noticed that you've got this real noisy transient response, right, that has this sinusoidal portion to it, and then that damps out as time goes on, right? And you're left with just the final oscillation, right? Sorry, this happened last week. Sorry. Forgot to change it between classes. My apologies. Right, so if we have damping present in our system, then our natural response, right, our natural frequency will eventually die out, right? Because the natural dynamics of the system will eventually reach steady state. And when that dies out, there will still be a remnant oscillation due to that input that is happening at the same frequency as the input. Okay, so if I think a good way of demonstrating this, right, is if you have you guys ever like have a jump rope when you were a kid and tie it to something and then start doing the wave with it? you're giving it an input of, whatever this frequency is constantly, right? And as you watch it, it'll start as a large wave that will die out, but it'll still be a wave, right? It'll just be smaller amplitude, okay? But it has the same frequency. It's just dying, like the amplitude is dying is what's dying, but this frequency remains the same. When we apply a sinusoidal input, we maintain that frequency even when we get to steady state. Okay. Frequency response is defined as the steady state response. So if you are asked to find the frequency response, you are being asked for the steady state response of the system. For these systems, we are not going to be talking about the transient response at all. We are simply going to be discussing the steady state response, because that is, by definition, what the frequency response is. It is the steady state response of the system to a sinusoidal input. If you have a linear system that we are driving with a sinusoidal input, the input frequency omega is the steady state output frequency, right? So if you have something that's oscillating as an input with omega, the steady state output will have that same frequency. Will still oscillate at omega. In general, the output sinusoid will have a different amplitude. So what happens, right? Going back to this jump rope example, right? What happens as we reach steady state here? Our amplitude is decaying, right? The amplitude is decaying as we get further away from the source. So basically, whenever we apply a sine wave to something, what we expect to get out is we will get a scaled version of that sine wave that will be shifted in time, right? So we will have some phase angle and we will have some amplitude change, right? The nature of the linear system, right, or the transfer function, right, determines the amplitude ratio, y naught to u naught, and the phase shift. And these quantities will be a function of the input frequency. So I'm gonna go ahead and do this, because this one's important. I know it's in purple, but now it's also in a red box, so it's extra important, right? Turns out that these two parameters, the amplitude ratio and the phase shift, are all that we need to know, right? Characterize our frequency response system. We can use these two parameters solely to determine the frequency. If you know the phase shift and the amplitude ratio, then you can come up with the steady state response for the system. This is also the basis for Bode diagrams. Now, you guys should have seen Bode diagrams somewhere along the way before getting here, we're hoping, right? A Bode diagram does what? It graphs how the phase changes as a function of frequency, right? It graphs how the magnitude changes as a function of frequency. The amplitude ratio is just the magnitude of that change, right? So if we know magnitude and we know phase, Dr. D claims that we know everything that we need to know to develop our frequency response. Yes, that is what I claim. Okay. Everybody cool so far? Today's going to be a lot of setup, right? Today's going to be the setup. We'll do a problem at the end, but it's mostly the setup today. Anything? Questions? Okay, so this is what it looks like. I put some sine wave in, right? And I get a sine wave out, right? This sine wave has a different amplitude, and it has been phased here. Right, so in this case, right, the solid line, right, in this case, the solid line is my input. And we'll say that the red line is my output. Okay. So the black line is my input, the red line is my output. And by going through the transfer function, I have decreased the amplitude of this sine wave and I have shifted it in time, right? Well, what about this right here? How much shift is there? What is the time shift? Time shift is the magnitude of phi, which is my phase angle, divided by omega, which is my frequency. Do the units check on it. Would you have radians divided by radians per second? The radians cancel, just left per second, 1/2 yeah. Okay. So this is what a phase shifted signal looks like, right? What if you shift by 90 degrees? Or the from sine to cosine. Okay. There's bigger implications to that that we'll go through later, right? Because that is related to a time delay, right? The more phase shift you have, the more delay you have in your system, right? Do you have any questions so far? No, everybody's doing all right. Oh, okay. Let's talk about the sinusoidal transfer. So let's, for a minute, use this as our example. This function here, this third order system, y triple dot plus 4y double dot plus 12y dot plus 46y is equal to 2 u dot plus 3 u. Now let's assume that we are going to apply an exponential input to this system, where s, so now we're in the Laplace space, right? U of s. We're going to say that s is sigma plus j omega, right? It's some complex number. Now, if we assume that zeta is 0, or I'm sorry, sigma is 0, and we're going to say that the real part is 0. Okay? Why are we saying that? Well, remember, the real part determines the exponential function, right? And as we approach steady state, that exponential function is going to go away. So at steady state, the effect of the real portion is gone, right? At steady state, sigma is 0. And so we're just left with s is equal to j omega. So I'll plug that in here, right? So u of t is equal to u of j omega e to the j omega t. Okay, and if I use Euler's theorem here, Euler, whatever you want to call them, right? Euler's theorem, I can take that e to the j omega t, and I can bring it down and make it cosine omega t plus j sine omega t, which gives me a real and an imaginary. Now, we went over briefly Euler's theorem when we talked about Laplace transform, right? We kind of did it in passing. And we're not going to go super deep into it right now, but this is really what we need to know is that e to the j omega t is equal to cosine omega t plus j sine omega t. And what implication does this have for us? How are we supposed to know that that's the real, like, can we trust this, right? Well, imagine for a second that we have everything we have in the real imaginary plane, right? We're in the S-plane, right? We're in the S-plane, and I have some vector that's defined by e to the j omega t, right? Well, the angle from the real axis is omega t. And that means that the real portion is defined by the cosine, and the imaginary portion is defined by the sine, right? So if the input is u of t is equal to u of j omega e to the j omega t, then the steady state particular solution, right? So back to differential equations, has to be y j omega e, y of j omega e to the j omega t, where y of j omega is also a complex function. All right. So that's Euler's theorem. Right? Euler's theorem. So where do we go from here, right? Because we want to make the sinusoidal transfer function, we're going to assume, right, that the transfer function is still the ratio of the output to the input, right? Because that's by definition what the transfer function is. So if we come back to this, right, we would say that this would be our transfer function, right? If we took the transfer function of our original equation, right? Take a Laplace transform with zero initial conditions, and I form my transfer function. I'd be left with this: 2s plus 3 over s cubed plus 4s squared plus 12s plus 26. If I look at the characteristics, right, I have one real negative real root and one negative real portion complex conjugate. Okay. Okay, so I'm going to substitute the exponential input and output equations into my differential equation, right? So I'm going to give this the full differential equations treatment. Remember, I'm solving for the particular solution here. I have determined that the particular solution takes the same form as the input, right? And in this case, we used e to the j omega t, right? U times e to the j omega t. That is what we use. So remember, going back, I'm using this, and I'm using this, okay? My input, and that's my output, right? Because it's a particular. In order for me to put that back into this equation here, right, I've got to take some derivatives of those functions. I've got to take 3 derivatives of the y equation, and I've got to take 1 derivative for the u equation. Right? And I can plug those in, and that's what I'll get on the bottom line. Right? Bottom line is j omega cubed plus 4 times j omega squared plus 12 j omega plus 26, whole thing from y j omega e to the j omega t is equal to 2 j omega plus 3 times u of j omega e to the j omega t. Right? So that's kind of gross. That's what we end up with. Now I have to make the transfer function, right? So I've got to get y of j omega over u of j omega. So there is the equation again on the top there. And I'm going to make the transfer function. Well, look here. This e to the j omega t, it's on both sides. It cancels. And what's with that? That looks really familiar. Right? Function. The sinusoidal transfer function is y of j omega over u of j omega. And that looks really familiar, I hope. Because we saw something on the previous slide that looked really a lot like it. And I'll show it to you right here. You spot the difference between these two transfer functions. What's the difference here?
You made S equal to J omega.
There it is. There's no difference other than S is equal to J omega. So turns out that the sinusoidal transfer function is the same as the normal transfer function, but with J omega instead of S. So when, this is not an if, when you are asked to find the sinusoidal transfer function, when, just find the regular transfer function and substitute in J omega for S. We did the long derivation. You know that it's true now. Just do it. Why do we want this as the sinusoidal transfer function? Well, we'll get there. We'll get there, right? We'll get there. But this is how we go about it, right? This is my sinusoidal transfer function. Again, how is this helpful? Well, this is going to help us create our steady state response, right? Our frequency response equation. Okay, does anybody have any questions right now? Nobody, everybody's good? Now remember, I told you a few slides ago that really all that we need to characterize this is the magnitude and the phase angle, right? It turns out, well, how do we find the magnitude? How do we find the phase angle, right? Well, guess what? The magnitude of my sinusoidal transfer function is just the square root of the sum of the squares of the real and the imaginary portion. So, Dr. D, are you telling us that I just need to find the resultant of this vector? Yes, 100% what I'm telling you. Now, let me ask you this, right? Remember, let's do it this way. Short this way, right? G of j omega is equal to y of j omega over u of j omega, right? So if I take the magnitude of this, isn't that just the same as taking the magnitude of the top and the magnitude of the bottom? So in our case, we had, wouldn't we just have the magnitude of 2j omega plus 3 over I forget what the rest of them are. Sorry, I dropped the ball. I forgot what the example was. But the point is this. You can take the magnitude of the top, which seems easy, right? Because the magnitude of the numerator here is just going to be 2 squared plus 3 squared square root, right? And you also take the magnitude of the bottom. This one's a little trickier because j cubed is actually negative j, right? Because j squared is negative 1, okay? So this term actually isn't complex anymore because j squared is just going to give you negative 1, right? So this becomes negative 4. This one becomes negative j omega. Okay. We'll do an example later, but just keep that in mind when we're working, right? So it turns out that you can take the magnitude of the top and the bottom. Well, what about this angle phi, right? This is my phase angle. My phase angle is how far I am off of the real axis, right? And the phase angle can be found by taking the tan inverse of the imaginary portion divided by the real portion. Now, what you'll see in a lot of cases is this polar form, right? And the polar form tells me that g of j omega is equal to the magnitude times e to the j p, okay? So let's come back here. Well, if I write this as the magnitude e to the jp, isn't this also have to be the magnitude e to the j, we'll call it p1, the magnitude of u, because it doesn't have to be the same angle. No, and instead of 1 and 2, let's call it numerator and denominator. Right? P numerator, P denominator, right? Okay. But can't, by the rules of exponents, can't I just say that that's just e to the j p numerator minus p denominator? Well, if I divide two things that are exponents, can I just subtract them? And that's interesting, because then you end up with e to the jp is equal e to the j p numerator minus p denominator, or which is just the tan inverse of the imaginary over the real portion of the numerator minus the tan inverse of the imaginary over the real portion of the denominator. And that's going to get us our phase shift. We still haven't talked about how to find the steady state portion. Yeah, still haven't talked about that, and we'll get there in a second. Do you guys have any questions on this? Because being able to write this in polar form and do this, right, helps significantly. Right? Because when we want to start talking about finding the steady state response, finding the frequency response using the transfer function, which we will have to do, first thing we need to do is find the transfer function. Then we substitute in j omega for s. Then we find the magnitude and the phase, right? And this is how we do it. Setting it off like this. Okay? So we want to derive an equation for frequency response that will automatically give us the steady state output of the system. Right? That's what we want. So this is where we're going to start with the block diagram. Right? I've got some transfer function. I put in an input and I get an output. Right? Transfer function times input equals output. Okay? That's what we have written here. Right? Transfer function times input equals output. Okay. And now we're going to take this transfer function, and we're going to rewrite it in polar. We're going to rewrite this in the polar form. Right? So what do we end up with? Right? Well, we'll end up with y of j omega e to the j omega t is equal to g, magnitude of g, j omega e to the j t times u, j omega e to the j omega t. Or, we'll end up with this. We end up here. Right? And so we can say that y steady state is equal to the magnitude of g omega, e to the jt, times u of j omega, e to the omega t, j omega t. And we use our exponent properties. You guys can start seeing, I think hopefully you're seeing what's going to happen here, right? So I've got e to the j omega t plus b, right? Why is that a big deal? Well, because if we use Euler's theorem, right, we can break it down into a sine and a cosine. And as it turns out, if we have a sine input, a sine wave input, then we're only going to use the sine output. Okay? So for a sine wave input, y steady state is equal to the magnitude of my sinusoidal transfer function times the original amplitude times the sine of omega t plus p. This is big. This is a big equation that is really important, and you need to know how to use it. How do we find the magnitude? We just went over it slightly. We'll do an example where we see how to do it in a minute. How do I find the phase angle? Same way. But guess what? If you're given a Bode diagram and you're told what your operating frequency is, you can read off the phase angle and the magnitude directly from it. So knowing how to read a Bode plot is super helpful. And we'll go over that too. We can go over how to draw them using the asymptote approximation method. I'll start that next class. Okay. But for right now, this is really important. So what if, Dr. D, I don't have a sine wave, I have a cosine? Great question. We're going to use cosine. You have a cosine. The best way to think about it is this. If I put a sine wave in, I will get a sine wave out. If I put a cosine in, I will get a cosine out. Okay? What is this telling us? This is saying that by going through the transfer function, I have scaled my input, right? This is my original amplitude, and I'm multiplying it by some factor. So I'm going to scale the amplitude, and I'm going to shift in time, right? That is what this is telling me. This equation has been boxed on two separate slides. It is important. It is the first equation in the frequency response section of the math system, right? You're gonna have to use it. You're gonna have to use it. In general, right, the general form of this is you write it with a sign. So just be cognizant of what your input actually is. All right. We good. We good on this. Everybody feeling all right? There it is again. There again. 3 times. All right. So therefore, the steady state response to a sinusoidal input is also a sinusoid with the same frequency as the input for a phase shift. Okay. We just went over this. Right? We just went over this. Well, it's here again, right? The magnitude is just the magnitude of the numerator and the denominator. Right? When you get the magnitude, right, you're just getting a scalar value, right? You get the magnitude, you're just getting a scalar value. So you do it for the numerator, you do it for the denominator, and you do the math to condense them. You'll get a single scalar value. That scalar value is used to scale your input. and then use arguments for tan inverse of your imaginary divided by your real to get to the rest. Okay. Let's just try one. Okay. So we have this RL circuit, and I want to determine the frequency response. Well, determine the frequency response, that means that we are going to find the steady state response, right? That's what it means. What's my input? 2 sine 50t. I've got a resistor of 1.2 ohms and an inductor of 0.02 Henry, right? So there's my diagram. Input in, output I sub L. Here's my truths, right? R is R, L, EL is L, I dot L, EN is equal to ER plus EL, right? We've done this model quite a bit. You guys start to get the feeling that you're just solving the same equation over and over again, and you have been for like the past 13 weeks. So, me too, except it's more than 13 weeks. All right, so here we are. All right, we've got our truths. I'll do the reduction starting on the next page. How do we do it? Well, we start with KVL. We start with that KVL. From KVL, almost spilled all my notes. That wouldn't have been good. From KVL, we end up with E in of T is equal to L, I dot L plus R, I. There's the reduction. It's done, right? If I write this in standard form, that is a first order system. I can write this in standard form. No, sorry, that's 1.2. So from the standard form, I know that tau has to be equal to 0.0167 seconds. And therefore my settling time is 4 times that, which is 0.067. Remember, in standard form, we have this, right? That's what our standard form for first order equation looks like. Tau y dot plus y equals a u of t. Okay, so there we are. We've got that. Okay. So let's do the Laplace transform. All right, we want, remember, the equation we're trying to satisfy, right, I'll write it up here, YSS is equal to G of J, magnitude of G of J omega, U naught, sine of omega t plus b. We need the transfer function so we can find the magnitude and the phase. So I got to take this, right? This is going to give me 0.0167 s plus 1 I sub L of s is equal to 0.833 En. We'll change this to En of s. Right? Remember, we're forming the transfer function. And the transfer function needs us to leave our input alone. We do not put our input in. for the transfer function, right? This is important because if you were to put in the Laplace transform of 2 sine 50t, you're going to throw everything off. To get the transfer function, I just need IL of s over En of s, which is going to give me 0.833 over 0.0167 s plus 1. There we go. Okay. So I've got this, right? This is fine. Now what? Now I need it to be a function of j omega. So I plug in j omega, right? Because now this is g of j omega. And if I want the magnitude of g of j omega, that's going to be, well, 0.833 squared plus 0 squared, right? Because it's the real squared plus the imaginary squared square root. There's no imaginary part here. Right, so last time I checked, this should be 0.833. Then you get 0.0167 squared plus 1 squared, square root. Well, if you do that out, 0.0167 to the 2 plus 1 to the 2 square root 1.00 gives me 0.833. So that is the magnitude. That is the magnitude of my function. Did I give myself another slide? Let's find out. Oh, I did. Happy day. All right, so remember, I would like the exercise now, please. Thank you. Remember, YSS is equal to G of J omega U naught sine omega t plus b, right? And we just found this. So now we need to find phi, right? And phi is equal to the tan inverse, right? We went over this on the previous slide, of the imaginary divided by the real of the numerator minus the imaginary divided by the real in the denominator. All right, so tan inverse of 0 is 0. Tan inverse 0.0167 over 1 is 0.0167. We've got a negative phase shift. So now I've got this, right? My original amplitude was 2, right? Because remember, En was 2 sine of 50t. That's omega. That's u. So now my steady state is going to equal 0.833 times 2 times sine of 50t minus 0.0167. or so that's 1.66. That's my steady state response. So all of this hinges on whether or not we can calculate magnitude and phase by hand, or whether or not we're given a Bode diagram and able to pick off those points using our Bode diagram, right? One or the other. Like I said, next class, we will focus on starting how to draw Bode diagrams using magnitude and phase, right? So we're going to start off drawing them by hand, right? Spoiler alert, in the real world, you're not going to really ever draw them by hand, right? If you need to do an analysis with them, you'll actually have a program pop it out for you. But understanding what it's supposed to look like and getting an idea of what it is supposed to look like is valuable. You guys have any questions? This is what it looks like. If you guys wanted to go into Simulink and model this, you could. So the solid line is the input. You can see we're phase shifted. We're phase shifted and our amplitude has shrunk. Any questions? You doing okay? The whole goal of topic 6 is understanding how vibrations impact our systems and how we handle them. And really, how can we design to attenuate vibrations in most cases, right? Mostly mechanical and biomedical engineers don't want any vibrations around. Right? We would like to eliminate them. So how do we design something that will eliminate vibration, and what is the design trade-off for doing so? Because there's always a trade-off. There's always a trade-off. That's it. That's it for today. Next class, Bode diagrams and some examples, right? Probably run a couple examples at the beginning of class. Have you guys do some. Why should I have all the fun?